Hello and welcome to Chapter 7.3 from Stevens' Introduction to Statistics, the Think and Do book. In this chapter, we're going to estimate a population proportion from a sample proportion by way of making a confidence interval. And in addition to that, we will figure out how to calculate a minimum sample size to create an interval which has a constraint on, say, the maximum margin of error. All right, so let's get started. I'm going to put this into full screen mode and full width. Okay. So again, we're going to take a sample proportion and we're going to estimate a population proportion. And let me, just in case you're wondering about proportions, because we haven't spent a whole lot of time on that, let's just look at this example first. A local company conducts a survey where people watch an advertisement which contains a phone number. Afterwards, they are asked to pick the phone number from a short list of numbers. In a random sample of 1,512 respondents, 474 picked the right answer, and 1,038 did not. And so the goal here is to find a 90% confidence interval, or an estimate, for the proportion of all people. Right? So we're not just going to use the sample proportion. We'll start with the sample proportion, but then we'll try to make an estimate for the proportion of all people who can correctly choose the given phone number. Right? So we'll have a sample proportion, and we're going to try to create an interval estimate for the population proportion. Okay, so that's what we mean by proportions. All right, so here's the terminology, right? P with no hat, just a small p, will be the population proportion. That is unknown, right? That's what we're trying to estimate. P hat, the sample proportion, is it's the point estimate for the population proportion. So if I get a sample proportion, that is what I call the point estimate. But we're going to do better. We're going to create an entire interval estimate. And if you don't have, if you're not given p hat, you can generally calculate it from the problem. In terms of x successes in n trials, p hat is the number of successes over the number of trials. And if you go to that example that's actually ahead of us here, what we have is 474 people picked the right phone number out of 1,512. So p hat is just 474 over 1,512. Right? So that's what I mean by x over n. Right? So you might not be given the specific proportion, but you will be given the number of successes and the number of trials. Q hat is 1 minus p hat. And by the way, I'm giving all this information looking ahead to this calculation for the margin of error. Because this process is identical to the last chapter. We get a sample proportion, we subtract a margin of error and add a margin of error. The process is identical. The margin of error formula is a lot different. So all these things I'm defining here, I'm aiming towards this, which has p hats, q hats, and a critical value. So p hat, sample proportion. Q hat, 1 minus p hat. Sample size is n. The confidence level, again, we'll be usually dealing with one of our popular 3 confidence levels. It represents the success rate of the procedure or the confidence that we have in our interval estimate. Alpha, which is 1 minus the confidence level in decimal form, represents the area and the 2 tails of the distribution of sample means. In this case, it's the normal approximation to the binomial distribution, but it represents the area and the 2 tails. And z sub alpha over 2, again, is just a name for a critical value of z. Essentially, it's called a critical value of z sub alpha over 2 because each one of these tails here contains alpha over 2 in terms of area. So z sub alpha over 2, there's a negative and a positive, right? So that's why it has such a funny name, right? And then E, the margin of error, is given by this formula. It's the critical value z sub alpha over 2. The sample proportion, 1 minus the sample proportion over the sample size. All right. Requirements. If there's a sample involved, it needs to be a random sample, a simple random sample. The conditions for a binomial distribution should be satisfied, and those conditions, as a little reminder, we have a fixed number of independent trials, having constant probabilities of individual successes, and we categorize it into 2 possible outcomes, success and failure. All right, so we are actually dealing with a binomial distribution. We're just using a normal approximation. So in using that normal approximation, there is actually one more requirement. I need at least 5 failures and at least 5 successes. That's equivalent from the requirement from, I think, chapter 6.5, where n times p hat and n times q hat have to both be greater than 5. Right? You don't have to worry about that. You just have to make sure that in the problem, you get at least 5 failures and 5 successes. All right. Calculating the confidence interval. The procedure is identical to the last section. I need to determine my confidence level. Not the confidence level, the critical value. We denote that with z sub alpha over 2. And if you're dealing with one of the popular confidence levels, you can use the small table below the z table. All right? And that small table is located right here. Right? Okay, let's go back. So getting that critical value is pretty easy. I'm going to calculate the margin of error next. And that comes straight from this formula here, 7.5. And then you determine the confidence interval, which means you just take the sample proportion, subtract the margin of error, take the sample proportion and add the margin of error, and that is your confidence interval. Only instead of having a mu in here, we put in p because p is what we don't know. That's the population proportion. So that's what goes in between the 2 interval limits. Concluding statement, I am, say, 95, 99, or 90% confident that the proportion, or you can use percentage, of all whatever it is we're talking about is between, and this is where you put in your bounds. Your limit bounds go in here, right? Okay, round-off rule. When we're talking about proportions, they're sort of like probabilities, so we're going to round these confidence interval limits to 3 significant digits, right? And the way you count significant digits is you start from the left, and the first non-zero is the first one, and then the next 2 count as the remaining 2 significant digits. So simple form, 0.123, and again zeros count, so that 0 counts as the 3rd significant digit. Preceding zeros don't count, so you don't actually start counting 1, 2, 3 until you get out to that 3rd decimal place. And internal zero. So once you get to this first non-zero term, or digit, you do 2 more, and that's 3 significant digits. Okay, so now we'll go back to the example and actually do it. So here's the idea. We work for a phone company, or not a phone company. This company actually sells vanity phone numbers like 1-800-Flowers. So they want to know how well people remember random phone numbers, so that way if they can say people are no good at remembering phone numbers, they can try to sell you a vanity phone number for a fee. So they conduct a survey where people watch an advertisement that contains a phone number. Afterwards, they are requested to pick that phone number from a short list of phone numbers, right? So the correct phone number is sitting in there somewhere. And in a simple random sample of 1,512 respondents, 474 picked the correct answer and 1,038 did not. So we're going to try to find the 90% confidence interval for the proportion of all people who could correctly choose the given phone number, right? We have a pretty big sample. So it's worth checking out the requirements. The requirements are a random sample, and it states here this is a simple random sample, so that's good. The conditions for a binomial distribution have to be met, so there's n trials, so there's n trials, 1,512 respondents. They're independent. Whether or not one person can pick the phone number correctly does not alter the probability of the next person picking the phone number correctly. The probability of success does not change. There's always the same short list, so everybody has the same initial probability if they were just guessing at it. And what else? Oh, success and failure. So there's two options. Success means they got it correct, and failure means they did not. So we got all of the requirements. Oh, wait, there was one more. We need at least 5 successes and at least 5 failures, right? And if you look, we have way over that. We have 474 successes, 1,038 failures. So we're good. All the requirements are met. Let's see what we can do here. We're going to do some preliminary information. P hat is x over n, which is successes over trials. 474 successes. There's 1,512 trials. So P hat, rounding to 3 significant digits, is 0.313. Q hat is 1 minus that, so it's 0.687. And n is the sample size of 1,512. And I peel those out because I'm looking at this margin of error formula. So I'm going to need P hat, Q hat, and n. But I also need the critical value z sub alpha over 2. But that's step 1, right? I'm looking at the 90% confidence interval, 90% confidence level. That's one of our popular ones. So it's easy to find the critical value, 90.9 on the confidence level, 1.645 is my critical value. So I have z sub alpha over 2 is 1.645. So now I just plug all these into my formula, right? I have the critical value, the sample proportion of successes, 1 minus the sample proportion, and divided by the square root of n. Don't forget to take the square root of the whole thing. And when you do that, and do that correctly, and it's a little tricky in your calculator. You have to use some extra parentheses, perhaps. You get 0.0196. And it's worth pointing out that for proportion problems like this, like we have here in Chapter 7.3, this margin of error will always look pretty small. You'll never get a big one because it's a proportion. So for starters, it's less than 1. And since it's a margin of error on a proportion, it's usually quite a bit smaller than 1. So 0.0196, it looks small, but it's not all that small once we convert everything to decimals. Okay, great. So the confidence interval, the upper bound is found by taking the sample proportion, and this is the lower bound, or the lower limit. We take the sample proportion, p hat, subtract the margin of error, right? And we get 0.2934. The upper limit, we take p hat, the sample proportion, and add a margin of error, 0.3326. So our confidence interval, there's our lower limit, there's our upper limit. We stick a p in there signifying that the population proportion, which is not known, we suspect is between these two values. Right? So the concluding statement, I am 90% confident, that's my confidence level, that the proportion of all people, not just my 1,500 that were in the sample, 90% confident that the proportion of all people who could correctly pick the given phone number is between 0.293 and 0.333. So that sounds a little formal, and it might be more formal than what you're looking to do if you were, say, making a flyer or putting this as a note in your advertisement. So you'd probably say something like this. You wouldn't use all the decimals, and you'd probably use percentages. You'd say between 29 and 33% of us can pick the right phone number, right? And you don't usually see the confidence level when people are writing confidence intervals. We will in this class because it's a statistics class, but in general, in publications and in flyers, they generally won't give you that information. But you should always be looking at least for some sort of interval. All right, for the your turn problem, it is the same problem, only I'm asking for the 95% confidence interval. Right? So we start off the critical value of z. Again, that's one of our popular critical values. So when you go to the z table and look down here, 0.95, critical value is 1.96. Right? Easy. Easy peasy. Right? 1.96. The margin of error comes from this formula. And we have the same p hat and q hat from the previous problem, and the same n. So the only thing that changes is the 1.96, right? Because we went from being 90% confident to this problem, which is 95%. And when you plug all those numbers in, you get a margin of error of 0.0234. And this is at the 95% confidence level. If you looked at the 90% confidence level from above, we had a margin of error equal to 0.0196. 0.0196. So notice, as my confidence level increased, my margin of error increased as well. Okay, to create the confidence interval, the lower limit is the sample proportion minus the margin of error. The upper limit is the sample proportion plus the margin of error. So I get these as my limits, and my confidence interval, I just take my upper and lower limits, stick p in between there, representing the population proportion, which is unknown, but we suspect it is between 0.290 and 0.336. The concluding statement: I am 95% confident that the proportion of all people who could correctly pick the given phone number is between 0.290 and 0.336. And you can put a more practical flavor on this and say, we estimate that between 29 and 34% of us can pick the correct phone number. But for a stats class, we're looking for a little more rigor in our concluding statement. And notice what happens to the margin of error when the confidence level increases. The margin of error gets bigger. It gets bigger, right? If you want me to be more confident, my margin of error will get bigger. My confidence interval will get larger, right? And again, that's the accuracy versus confidence. You have accuracy and confidence. They are not the same. In fact, they are inversely related. If you want your confidence to go up, your accuracy will go down. Right? Important observation, often confused. And this is just because this is a real problem, I thought it was worth mentioning this. There were only 5 phone numbers on the short list, right? And so if you just randomly guess, if you didn't even try to remember the phone number, 1 in 5, there's a 20% chance of randomly guessing the phone number correctly without any thinking, without ever even seeing the ad with the phone number. And what we see from the from this little survey is that between 29 and 33% of us can pick the right phone number. That actually is worse than it sounds, because 20%, monkeys could hit 20%. So we're only about 9 or 10% above random guessing when it comes to recalling phone numbers, which makes sense. I have trouble recalling phone numbers. Okay, now down to calculating sample size, just like we did in the previous chapter. And here's sort of the setup. Suppose I got to this margin of error, right? Go back here. Here's our margin of error, 0.0234 at the 95% confidence level. Suppose I said that's too big. I want a smaller margin of error. I want a more accurate estimate. And to do that, I'm going to have to take a larger sample size. And the question is, how much larger? How big of a sample do I need? And we can answer that question by going back to the formula for the margin of error for our population proportion. And notice that our sample size is sitting over here. So if we solve that equation for n, we get equation 7.6, right? And the problem is, if we haven't conducted the study yet, we won't know p hat and q hat. But because these things add up to 1, there is actually a maximum value that that product can be. In fact, the maximum that can be is 0.25. Little trick from calculus. So if p hat and q hat, well, if p hat is known, you want to use this first formula, 7.6. And if p hat is not known, you replace the p hat times q hat with 0.25. Really quite simple. And again, this gives us the minimum required sample size for a given upper bound on the margin of error. So E in here, it's in both places, E in this formula equals the max margin of error. Right? What are you willing to tolerate as far as error goes? Right? And again, the sample size does not depend on the population size. There is no minimum percentage of the population required to get an accurate estimate in the sample. Okay, round off rule for sample size, next larger whole number. So if I get a decimal here, then I want to round up. Right? Always round up. So our example, similar to example 1, this is example 2, only now it's a sample size problem. We're going to consider the previous example on the previous page. And the company wants to conduct another survey, but wants an estimate of the sample size. Right? It wants to reduce that margin of error. Right? So we're going to ask this in a couple ways, but the first way is, what is the minimum sample size required if the company wants to be 95% confident that the sample proportion is within 2 percentage points of the population proportion? What that means, 2 percentage points, means that E is going to be 0.02. Remember to write a percentage point in decimal. Right? If you write E as 2, your answer is going to be way off. And we will assume that we know p hat from the previous study and set it equal to 0.313. Right? So because I know p hat, I'm going to be using this first formula here. Z sub alpha over 2 squared, p hat q hat over the margin of error squared. So that's right here. Right? And if I'm at the 95% confidence level, my critical value of Z is easy to find. It's one of the popular ones. 95%, it's 1.96. Right? So we go back. So Z sub alpha over 2 is 1.96. P hat, I'm told, is 0.313 from the previous example. Q hat is 1 minus p hat. Right, this is p hat. This is q hat. Let me make that a little prettier for you. Q hat. And then the tolerable margin of error is 2 percentage points. So my capital E becomes 0.02. And when I plug all those values in, I get a minimum sample size of 2065.2. And since I can't get a sample size of 2065.2, I always round up whenever I have a decimal. So I need 2066 people if I want to have a margin of error which is less than 2 percentage points. Right? So that should do it for us. Okay, so your turn. Same question. What is the minimum sample size required if, and I'm going to change some of these constraints. I want to be 99% confident, so I'm going up in confidence. that the sample proportion is within 1 percentage point. So my margin of error is 0.01. And I'll assume that I don't know p hat, right? Because p hat might change in this next sample. So I'll assume I have no idea what p hat is. And since I don't know what p hat is, I'm going to use this second formula, right? Where the p hat times q hat gets replaced with the 0.25. All right, so z sub alpha over 2, this is the 99% confidence level. So I go to that little table, 99% confidence level. I have a critical value of 2.575. Right? Easy. That little table is really helpful. So there's the 2.575. I don't have p hat q hat. I replace it with 0.25. My maximum margin of error is 0.01, so that goes in there. I do all these calculations, and you should make sure you get this with your calculator because there's an order of operations issue that you have to make sure to follow, and some parentheses might be helpful for that. So in any case, when I plug this in, I get 16,576.56. That is a large sample. And again, you have to round up. So the company must select 16,577 people for the survey, which I doubt it will do. But notice what happened here. In the first example here, we had a minimum sample size, in fact, this one, 2,066. That went up to 16,577. It got huge. And the question is, or the observation here, it got huge for 3 reasons. First, I used no assumption of p hat. So when I did this 0.25 here from the second of those equations, that's actually the biggest that p hat times q hat can be. So that got bigger. My confidence level increased. So that caused my critical value of z to get bigger. And then my margin of error got smaller, which meant this thing got smaller, which means the whole n. That's what really made it get huge, by the way. So my sample size got huge for 3 reasons. The most important reason is that my margin of error went down to 0.01. Because when you take 0.01 and square it, that gets really small, making the fraction very large. All right, so that's it for Chapter 7.3, Confidence Intervals About Population Proportions. I will catch up with you in Chapter 7.4. Bye now.